This is the shortest route from Los Angeles to Tokyo. At least, that's what the pilots and the flight planning computers will tell you. But take a closer look. The flight path doesn't go straight across the Pacific. It curves far to the north, near Alaska, before turning back toward Japan. If this is truly the shortest path, why does it look like a detour? What's even stranger is that this isn't just one unusual flight. Look at flights from New York to Beijing, from London to Vancouver, from San Francisco to Seoul. Again and again, you see the same pattern. Airplanes seem to ignore the straight lines our eyes expect. You've probably heard the most common explanation. Airlines avoid flying across the Pacific because it's simply too dangerous. Too much open ocean. Too few places to land if something goes wrong. It sounds completely reasonable. In fact, I believed it too, until I came across one detail that made the entire explanation fall apart. There are flights that cross thousands of kilometers of open ocean. There are flights that fly even farther north, across the Arctic. And sometimes, the exact same journey follows a completely different route from one day to the next. If safety were the only reason, why wouldn't every airplane fly exactly the same way? Clearly, there's another rule at work, a rule that most passengers never notice. And the fascinating part is, it doesn't just explain how airplanes fly. It explains why millions of people look at the same map and arrive at the wrong conclusion. Because before we can understand the flight path, we have to answer a much stranger question. What if the real problem isn't the airplane? What if it's the way we've been taught to see the Earth? At first, the explanation seems obvious. Airplanes avoid flying across the Pacific because it's dangerous. Too much ocean. Too few places to land if something goes wrong. It sounds logical. And for a long time, that's exactly what many people believed. But then, something doesn't quite fit. Every single day, airplanes cross enormous oceans. Flights from North America to Australia, from Hawaii to Japan, from Chile to New Zealand. Thousands of kilometers, with nothing but open water below. So clearly, crossing the ocean isn't the real problem. Maybe it's fuel. Maybe airplanes simply can't fly that far without refueling. Again, it sounds reasonable. Until you remember aircraft like the Boeing 787 or the Airbus A350. Modern airliners are capable of flying well over 14,000 kilometers on a single tank of fuel. More than enough to cross the Pacific. So if range isn't the answer, what is? The more closely you look, the stranger the mystery becomes. Different airlines often fly slightly different routes. Even the same airline can choose a different path on another day. If there were only one correct answer, why would the routes keep changing? At this point, it becomes clear. We've been asking the wrong question. The real mystery isn't why airplanes don't fly straight. The real mystery is why our idea of straight might be completely wrong. Imagine you're standing in front of a globe. Not a flat map, a real globe. Place one finger on Los Angeles, then another on Tokyo. Now try to connect those 2 points. Your instinct will probably tell you to draw a straight line. After all, we've believed one simple rule since childhood. The shortest distance between 2 points is a straight line. And on a flat sheet of paper, that's absolutely true. But the Earth isn't a sheet of paper. That's where everything changes. The mistake isn't in the flight path. The mistake is forgetting what we're drawing on. The Earth is a giant sphere. And when you try to place a 3-dimensional world onto a 2-dimensional surface, something unexpected happens. What looks like a detour may actually be the shortest path. Try a simple experiment. Take a piece of string. Stretch it between Los Angeles and Tokyo on a globe. You'll notice something surprising. The string doesn't cut straight across the Pacific. It bends north, passing close to Alaska, almost exactly like the flight paths we saw earlier. But here's the remarkable part. The string isn't taking a detour. It's following the shortest possible route across the surface of a sphere. Mathematicians call this a geodesic. In aviation, it's better known as the Great Circle Route. The name itself isn't important. The idea behind it is, on a sphere, straight doesn't look the way our eyes expect. On a flat map, the curve appears longer. But once you see the Earth as it really is, everything flips. The curve is the straight line. And that's exactly why this illusion fools so many people. Not because they misunderstand airplanes, not because they know nothing about aviation, but because every single day, they look at the world through something that quietly changes their perception, a flat map. But if the real problem is simply that the Earth is a sphere, another question immediately appears. Humans have known that for thousands of years. So why do most of the maps we still use today continue to make the world look so different from reality? Because the next piece of this story has nothing to do with airplanes. It begins with a map. If you open up any familiar world map, you'll likely see an image just like this. The Americas on the left, Europe near the center, Asia stretching out to the right, and the two poles of the Earth stretched out at the top and the bottom. It looks very natural, very familiar, to the point that we rarely ask, why does the map have this shape? Because there's a strange truth here. The Earth is a sphere, but almost every map we've ever looked at is a flat plane. And turning a globe into a piece of paper is not a simple task. If you don't believe me, you can test it yourself. Take an orange, peel it. Now, try to lay that peel flat on a table. You'll discover a problem. It will tear, or it will distort, or you'll have to stretch it in certain places. The Earth is the same. There is no way to put a spherical planet onto a flat plane without distorting something. You have to make a choice. Keep the distances correct, keep the area correct, or keep the shape correct. You cannot keep them all at the same time. And in the 16th century, a Belgian cartographer named Gerardus Mercator created a map that changed how humans see the world. It's called the Mercator projection. His goal wasn't to deceive anyone. On the contrary, it was an incredibly clever invention. Because for sailors crossing the ocean, this map had a huge advantage. It helped them maintain a constant bearing on long voyages. That's why it became an essential tool for hundreds of years. But there was a price to pay. To maintain those bearings, the map had to stretch the world near the poles. And the further you get from the equator, the greater the distortion becomes. That's why Greenland, on many maps, looks almost as big as Africa. But in reality, Africa is about 14 times larger than Greenland, a giant continent, shrunk in our imagination, while an icy island looks massive. And the same thing happens with flight paths. On a Mercator map, a curved route on the globe can look like a long detour. But when you put it back onto the true shape of the Earth, it becomes the most natural path. So the story was never just, why don't planes fly straight? The real story is, we are looking at a three-dimensional planet through a two-dimensional window. And every time we do that, we have to accept that a piece of the truth will be distorted. But the most interesting part is still ahead. Because even if you understand the map, there's still one question left. If the Great Circle is always the shortest path, why don't planes always choose the exact same route? Why does one plane fly near Alaska today, but another one chooses a different direction tomorrow? The answer lies in things that passengers almost never see. The massive currents in the sky, technical limitations, and thousands of invisible decisions behind every single flight. Now we know an important truth. The airplane isn't taking a detour. It's just following the true shape of the Earth. But that still leaves us with a question. If the Great Circle is the shortest path, why don't all flights just pick one route and fly it forever? Why can one plane fly near Alaska today, but another day choose a different direction? The answer is, the flight path isn't decided by a single factor. It's the result of thousands of calculations made before the plane even leaves the ground. Imagine a pilot preparing for a flight from the US to Asia. On their screen, there isn't just one blue line. There are dozens of different options: a shorter path, a more fuel-efficient path, a path to avoid bad weather, a path with more emergency landing airports. Every choice comes with a trade-off. One of the biggest factors is something passengers almost never see: the wind. 10,000 meters up in the sky, there are massive currents of air moving around the Earth. They're called the jet stream. An airplane flying with this current can be pushed much faster, but flying against it can make the flight take longer and burn a lot more fuel. That's why sometimes a flight that looks longer on a map is actually the faster flight in reality. Because the plane isn't just looking for the shortest distance, it's looking for the most efficient path. But there's another factor, even more important: safety. A modern airplane can fly thousands of kilometers over the ocean, but that doesn't mean it can fly indefinitely without preparation. Airlines have to calculate: what if an engine fails? What if the weather changes? If we need an emergency landing, where is the nearest airport? That's why ocean routes are always calculated with extreme care, not to avoid the ocean, but to ensure that even if the worst happens, there is a plan. To the passenger, it's just a curve on a screen. But behind that curve are thousands of decisions made to get them safely where they need to go. And here's the most interesting part: a perfect flight path doesn't exist. There's the shortest path, the fastest path, the most fuel-efficient path, the safest path. But they are rarely all the same thing. So, when you see a plane taking a curved route on a map, don't think it's going the wrong way. It's solving a puzzle with millions of variables: the shape of the Earth, wind, fuel, weather, technology, and human limitations. But perhaps the most surprising thing isn't how the plane finds its way. It's how something as simple as a map made us ask the wrong question from the very beginning. And that is the final piece of the story. There's something fascinating about this story. At first, it was just a very simple question: why don't planes fly straight? But the final answer isn't in the airplane. It's in the way we view the world. For thousands of years, humans have tried to shrink this planet down so we can understand it. We draw maps, we draw borders, we name the oceans. We divide the Earth into shapes that fit neatly on a sheet of paper, and that has helped our civilization grow. But every time we turn a three-dimensional world into a simple image, we also lose a piece of the truth. A curved flight path isn't a mistake. It's just a reminder that our perspective has limits. On a map, a curve might look like a detour, but on the planet itself, it is the most natural path. This doesn't just happen with airplanes. It happens many times in life. We look at a financial chart and think we understand the economy. We look at a photograph and think we understand the story. We look at a number and think we understand the truth behind it. But sometimes, the problem isn't that we lack information. It's that we're looking at that information from the wrong angle. Maybe that's why the story of these flight paths is so compelling. Because it's not just about airplanes, it's about a very human habit. We tend to believe what we see first: a straight line, a map, a simple answer. But the real world is often more complex than it looks. Next time you're on a flight and you see the flight path on the screen in front of you, maybe you'll realize something else. That plane isn't taking a detour. It's following the true shape of the planet. And perhaps the most amazing thing isn't that humans built machines that can fly halfway around the Earth. It's that after thousands of years of exploration, we're still learning how to truly see where we live.